On today, to 1221, the astronomy essential question is, how do massive objects move in gravity fields? We happen to be in Earth's gravity field right now, so that's what we're going to focus on. The first task is to calculate what the acceleration due to gravity is here on this planet. And so we'll consider Newton's law of universal gravitation that says that the force of gravity between two massive objects is equal to this, the product of their masses, times this constant of proportionality, Newton's universal gravitational constant, and then divided by their separation distance squared. And then Newton's second law of motion that says force equals mass times acceleration. So we'll use those two laws. Think about acceleration right here. This is kind of where it shows up in these equations. And so this is the thing that we want to solve for. If you think just sort of like with algebra, if this is the force due to gravity, I just heard a sound in my microphone here, which might mean that the microphone's dead, or maybe it just started working. I don't know. So if you notice the change in the audio, so do I. The force due to gravity is equal to mass times the acceleration due to gravity. Or you kind of think about it in terms of that. So algebraically speaking, if the force due to gravity is equal to this, and the force due to gravity is equal to this, what can we say about them? Any algebra people out there know kind of what we're getting to here. Like in math class, it's like, oh, y equals this, and y equals this other 5x plus 2, y equals 2x plus 1. What can we do with those equations? Set them equal to each other. Yes, set them equal to each other, whoever said it, because we can substitute like this in for this, right? Like if this is the force due to gravity, and so is this, well, we've got to be equal to each other. Okay, we can substitute in that way. So let's do that in, we want to avoid putting orange chalk next to blue in this lab. So we'll use, green, I just said much better. Why don't we do green? Let's see, green and orange would be what Miami. That's blue and orange. That's University of Florida, right? All the data fields. No, it's fine. Orange chalk is fine. All right. So let's do the working right here. All right. So we'll say, you know what? Let's do the working. So with those equations in mind, we've got the force due to gravity equal to G M over R squared. The force due to gravity equal to mass times the acceleration due to gravity. Or let's just tuck that side over there. So we're going to set these equal to each other. So the first step is to say that G M over R squared, which is the force due to gravity, must also be equal to M, acceleration due to gravity. Again, with kind of the setup here where like this is the Earth, this is some mass sitting on the Earth's surface, and we want to know how strong is the gravity field. The acceleration due to gravity is like a way to measure how strong is Earth's gravity field. How quickly does the gravity field accelerate objects is a way to measure how strong it is. Like on Jupiter, things accelerate more quickly, on that planet than they do here on Earth. That has a stronger gravity because it's more massive. It's also bigger, so it sort of spreads that mass out over a greater volume. But still, it's so much more massive that sort of wins. And so its gravity field is like 23. The value that we expect to get for this, like the known value, is 9.8. So we want to like, where does that 9.8 number come from? You sort of take the physics. Oh yeah, 9.8 meters per second squared. That's the acceleration due to gravity of the planet. Where does that number come from? So the first thing that you should maybe recognize mathematically is that it doesn't really matter how massive this is. Okay, it doesn't matter how massive you are sitting on Earth in terms of how strong your gravity field is. And mathematically, we can see like if we were to divide both sides by m, then it's going to cancel. Anytime you see the same variable on both sides of the equation, like in the same space, like they're both in the numerator, that just means you can divide both sides by that quantity. M divided by m is 1. 1 times this is just this. M divided by m on this side is 1. 1 times this is just this. So that's kind of what's going on. And we solved it. Right, we're done. The acceleration due to gravity is equal to all this over here. G m over r squared. And so that initial question that I posed a moment ago, what is the separation distance between you sitting on the Earth and the Earth itself? Think about that for a moment. How far away are you from the Earth right now? YouTube, leave it down in the comments below. I don't know everybody leave it down in the comments below. At the end of, we watched Dr. Don Lincoln from the Fermi Lab do a great explanation about, how could space be this big if it's only 13.7 billion years old. And then at the end of his, YouTube, he says all the same things I was here, like, oh, my son watches YouTube all the time. It's like, don't forget to subscribe, and hit the like button and all that. It's a true YouTuber right there. He's got it down. He's PhD in physics, but he's got his YouTube stuff. You guys were studying that social media the other day, right? Mental education.
Gotta plug it in.
You know about it. So this is going to be the mass of the Earth. You need to know that. And in fact, the experiment that was conducted by a gentleman named Henry Cavendish back in 1802, he was the first one to measure this constant of proportionality. They called that experiment weighing the Earth because once we do that, that's kind of when we could calculate, how massive the Earth was. We knew everything else in this equation, sort of besides that. So he devised a very clever experiment to sort of like measure the force of gravity between two masses, and we knew how far apart there was, like giant lead spheres and things like that, and kind of sort of rotate towards each other with a torsion bar. And then as soon as we knew this value, then we can sort of plug it back into the equation. So what's the mass of Earth compared to something else? So they call that experiment weighing the Earth. So that's kind of how we know this value. But again, how far apart are you from the Earth, e-learners? Oh, e-learners out this morning. Well, we got a lot to get to. We got an abbreviated schedule, so I'm not going to dwell on this point too much longer, other than to say the answer is not zero. So like I'm standing on the Earth, so I'm not separated from it at all. I'm 0 meters away. But then, like, no, zero divided by zero. That's a problem. Like, try it in your calculator. No, don't try it in your calculator. It will malfunction when you start. Sparks will fly out and be some kind of error message or something like that. So you can't divide by zero. So you're not 0 meters away. You have to sort of consider all the mass of planet Earth, which I'll give you the value now. 5.97 by 10 to the 24 kilograms. So yesterday we looked at like a single electron, it's like 0.00300911 kilograms. The Earth is a whole bunch of kilograms. Okay, 10 to the 24 kilograms. Makes sense, right? It's a giant collection of matter underneath our feet. So how far apart is some mass on its surface from that? We have to consider all of this mass of planet Earth exists sort of right here at the center. So mathematically, we can just kind of say, even though the mass of Earth is distributed over the surrounding volume of our planet, we can mathematically consider all of that mass to act at a single point, which would be right at the center of the core. And so that's the distance right there, the radius of the Earth. Okay, the radius of the Earth is how far apart you are from the Earth. If we just sort of approximate, all this planet underneath our feet is really right there at the core. Just like say all that mass is just located in a single point right here. That's not really true. But it's like the mass that's closer to you here is attracting you more, but the mass on this side is further away, attracting less. So it all averages out. So very brilliant mathematicians have kind of proven that that's allowed. And we can make that assumption safely. Who were those brilliant mathematicians? It's like Newton had a lot of laws, right? This is his second law. Oh yeah, he also had this law. Oh yeah, he's the one that figured this out. He invented calculus. So what is the radius of the Earth? Let's just say it's 6 million, 6 by 10 to the 6 meters. So here's 1 meter. And it would be 6 million of these down to get to the center of the Earth. So that's how far apart you can consider yourself to be from the Earth. So that's all we need, right? We've got the mass of the Earth. We've got how far apart some mass on Earth's surface is from the Earth. And the value of G, good old Henry Cavendish came up with back in a couple hundred years ago. We haven't done much better since then. Improving on this, 6.67 by 10 to the negative 11, a really small number that kind of shows how inherently weak gravity is. And then the units are Newton meters squared per kilogram squared. So let's make those substitutions over here. That might be harder to see. All right, so G, 6.67 by 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth, this number, 5.97 by 10 to the 24th. Sorry for the in-person just really see the whiteboard here. All right, 5.97 by 10 to the 24 kilograms, and then over r squared, where that's the radius of the Earth, which maybe I think like 5.97 by 10 to the, no, that's 5.97. It's close to 6, and it's like 5.94 by 10 to the 6. 6 by 10 to the 6 meters. So yeah, 6,000 kilometers, right? So 6 million meters. And then don't forget to square that. The meters squared, like when you square this number, you also square the units. So meters squared in the denominator, cancel these units. One of these kilograms here cancels this one. And so the units we get newtons per kilogram, that's one way to think about the acceleration due to gravity. Okay. The force in newtons acting per unit mass. And so we can kind of show that a Newton per kilogram, which again is like a way to say, on Earth, how many newtons act on each kilogram of mass? Yesterday I mentioned I'm 100 kilograms of mass. Remember the known answer is 9.8. So on Earth, we're saying every kilogram of mass has 9.8 newtons of force pulling down on it. So because I'm 100 kilograms, my weight, the force due to gravity that I feel, be up here on the surface of the Earth, is 980 newtons. That's my weight. Okay, in the units that we use in physics, newtons. It's a force, the force due to gravity. Okay, that's this poster here. Everybody in person's like, oh yeah, we can clearly see that. And everybody on YouTube is like, oh, we don't really see that. Do that. No, I'll move the camera up and move it. So 9.8 newtons per kilogram. But we're saying that that's the same thing as like on Earth, things accelerate 9.8 meters per second faster every second Earth's gravity acts on it. So like meters per second squared is the same thing as like saying there's a change in velocity per time. You know, like in America, we think about acceleration typically as like a car can go from 0 to 60 and change its velocity like that in 10 seconds. It's like, oh, it can accelerate that much. It's like the units are miles per hour per second. And physics is like meters per second. It's like any distance by time is a speed. And these are actually the same. So a meter per second squared is a Newton per kilogram. Because a Newton, if we go back to Newton's second law, a Newton of force, so these are quantities that are related: force, mass, and acceleration. We measure them in units though. So newtons of force are equal to kilograms of mass times meters per second squared of acceleration. So if a Newton is a kilogram meter per second squared, that's sort of, the Newton is a derived unit, like we mentioned in joules, a derived unit yesterday. These are all base units, kilograms, meters, and seconds. So a Newton, the derived unit, is equal to a kilogram times a meter divided by second squared. And if that's true here, then we can substitute that in. We can say, okay, 9.8 newtons. Oh yeah, but a Newton is really a kilogram meter per second squared. Kilograms cancels, meters per second squared equals meters per second. So a Newton per kilogram is the same thing. Okay, just a different way to think about it. You can either think about Earth's gravity field as being how many newtons of force are acting on each kilogram of mass at the surface, right? So, 980 newtons, but my mass is 100 kilos. There's some sort of numbers here. So therefore, so mass is how much matter I have. My weight on planet Earth due to this gravity field that we're sort of calculating is 980 newtons. But where did that 9.8 come from? Okay, so we got to sort of Maybe some of you already see where it comes from because there's the calculation right there. Right? Maybe you can't see it. So either a force per mass or an acceleration. How many meters per second things, speed up every second we allow gravity to act upon them. To make it more familiar, this is about 23 miles an hour. So you kind of know what it's like to travel 23 miles an hour in a car or something. So gravity will speed things up. Every second you allow it to act, it'll make it go 23 miles per hour faster. Right? So right there, we didn't even let it fall for a second. But if we did, we'd have to be like from the top of the 37 building. That's how high you need to be to let something fall for an entire second. And by the end of that, it'll be going 23 miles per hour. And if you could be high enough up to let it fall for 2 seconds, it'd be going 46 miles per hour, right? Every second it falls, it picks up 23 miles per hour of speed. So that's one way to think about the acceleration. That's over here. The acceleration of your gravity. All right. So crunch these numbers in your calculator. 6.67 by 10 to the negative 11 times 5.97 times 10 to the 24 divided by 6 million squared. So this is kind of tough to type in the calculator. It's like this square doesn't cancel. Gravity. Okay. So you might have to use like double parentheses, to get that square there. But it should come out to a number that rounds to this. But like what number exactly? Try that calculation for yourself if you want to. YouTube, you can pause the video if you're trying out for yourself because I'm going to reveal the solution. Well, I'm going to calculate it. I'm pretty sure I recall it off.
You just keep the calculator in your pocket?
Yeah, that's how cool I am. And one day you might have planned, goals of being as cool as me, face shield and all, but probably. Sorry.
It just says you're prepared.
Calculator in my pocket, chalk dust on my pants, dry erase ink through my veins. Okay, I'm a true teacher. Divided by double open parentheses 6 by 10 raised to the 6, close the 1, square it. That's not right. Let's try this. 6.67 by 10 raised to the negative 11 times 5.97 by 10 raised to the 24. So on the numerator, I go like 10 to the, or 4 by 10 to the 14 thereabouts, divided by 6 by 10 to the 6 squared. I'm getting 11. That's way off. According to this, it's 11.06, which means. All right, let's go ahead and ask artificial intelligence. Hey, Siri, what is the radius of the Earth? Oh, no. Hey, Siri, what is the radius of the Earth? Okay, so we have 3,963 miles. Okay. A mile is 5,280 feet and 3.28 feet per meter. So let's see how close it comes to that. And that will hopefully fix the problem. 3,963. So I think it's like, I was like, this is your quiz. Like, I'm in this gathering. I failed the quiz. I don't know what I did. It's like, why did everybody do so bad on the quiz gathering? Good, everybody. All right, so I'm getting now very exact value. It sounds like 6.4. Okay, we needed 6.4. So 6, 3, 7, 9, 4, 6, 3. There's just no way we can know it that exactly, right? Like, because it's not constant for one. There's some places where there's mountains, there's other places where there's trenches. So like on average, it's about 6.4. So like we can't really report it to more significance like this. how precisely can we get this? Keeping in mind that it's like an average, and we're assuming Earth is a perfect sphere. My brother, the geographer, would remind us that Earth is an oblong spheroid, but you know, physics, we can just kind of assume it's a sphere. It's easier. All right, let's check it again.
I Googled it, and Google says that the radius of Earth is 6.371 million meters.
So they have a 1 right here. So these digits here, that kind of emphasizes my point. It's an artifact of just like what my calculator says, these exact values would be mathematically. But it's too precise. It's what we say calculator value. It's not accounting for like uncertainties and measuring the Earth, right? So you can say, well, maybe I should kind of round it to, they say this is a 1 right here.
Yeah.
So we just say that's still rounded to 6.4. So let's just change this to, we were nearly good. So 6.4 by 10 to the 6. So we missed that 0.4 and it gave us an answer of 11. We don't live on a planet with a gravity field of 11, right? 9.8 is the number we want. And I think that should do it, right? Like if you've already checked that for yourself, like, yeah, that is something else. Now I'm sure it will. That's called test correction, which I allow in this class. Test correction.
It's not science if you don't make mistakes.
That's certainly right. All right, so, and really in experimental sort of science, it never works the way that we think it's going to. That's just always the case. 6.67 by 10 raised to the negative 11 times 5.97 by 10 to the 24th divided by 6.4. See, yesterday I made a whole big deal about using grouping symbols when dividing by things in scientific notation. Here I'm about to make yet another mistake. Okay. I'm embarrassing myself in front of YouTube. You can be like the first person in history to make a fool of myself on YouTube.
Well, if anyone comments on your YouTube, then you know.
All right, now I'm getting, I really wish it would round to 9.8. 9.72. Anybody else get that? That's following along at home? Yep, leave down a comment below. So 9.72 meters per second squared. And maybe if we put like the 371 or something like that, we get closer to the, because we're dividing by a slightly bigger number, which makes our answer smaller. So if you did it, you looked up like the known value of the radius of the Earth as accurately as we can know it, then I'm sure you get close to like, you can go for it if you want to right now and calculate this again with 6.371. And I'm sure you get even closer to 9.8, probably spot on. The point is, though, that it's not exactly constant even everywhere on the surface. There's places on our surface that are higher latitude, lower latitude, near the equator, because Earth is sort of like an oblong spheroid, which means it's a sphere that's been squashed at the poles, so it's a little bit fatter at the equator than this sort of the distance from the center to the poles is less than the distance from the center to out, so the equator and the center of the Earth. So closer to the equator, the gravity is a bit weaker because we're further away from that center point that we assume all mass is accurate. And so there is more sophisticated equations that can calculate what it is at different latitudes, at different elevations. So for sort of our purposes here, we're just going to assume that this number is 9.8 meters per second squared or newtons per kilogram, and that's the value that we're going to use for the acceleration of gravity. But so I know for your quiz, right, you're writing down sort of this calculation for your quiz work. This should be the answer that I see in your quiz to know that it's like you didn't just write down the known value. You actually, kept up with the calculation. So 9.72, even though I know it's not right. All right. Now, what can we do with this? How do massive objects move in this gravity field that's this strong? I'm glad that you do. All right, so the ultimate goal here is to be able to launch things and predict their motion. In a week or so, we're going to have, I think, like 4 rovers land on Mars. Okay, like different space organizations have all sent them different missions to Mars. And all. It's the same physics that we're exploring here. Like we launch something, okay, how does it move in Earth's gravity field? It's the same physics, just a little bit different. Like how do we launch something and get it to, loop around a planet and then go where we want to go, Mars or Pluto or whatever. And how profound that is shouldn't be lost on you, right? Like we can figure out here on Earth, how things move in gravity fields, and the same physics that allows us to, like predict where a marble is going to land. So that's what we're going to launch here. How far down the lab bench is it going to land? That's the same physics that allows us to launch rockets into space and then rovers on Mars. Pretty awesome. So here's the way these calculations look. We're going to launch something with an initial velocity vector. Okay, so it's going to have some speed v. We can measure that speed by sending it through the photo gate timer. The photo gate timer looks like this. So this is the sort of experimental setup that we have here. There's our marble launcher, and as it passes through this photo gate, the photo gate will record the time. And if I know the width of the marble, then I'd be able to calculate its velocity because it's traveled, the distance of its width over the time that will be recorded in the photo gate. So I can directly measure its velocity. If you look at that reading there, so I pinch the marble under the widest part, these are calipers, and then I can read like where the 0 is, just under 2 centimeters. And so we're going to call this marble 1.9 centimeters wide. If I launch this marble at 45 degrees, and there's different sort of notches that I can sort of, so there's a spring mechanism here, and I can make it, that much compression. Or if I spend more energy, I can compress the spring more, right? And so there's more energy stored in it here. And so that's going to deliver a greater force. And the greater force, the greater the acceleration. That's Newton's second law, right? So we want to measure how much velocity comes out at this one. And you can see also I can adjust the angle that I launch at. So that's going to be sort of another thing to consider. Gravity only acting in a certain direction. So gravity only acts in the vertical direction. It doesn't care about things moving horizontally. Yeah, we're launching today. And so my photo gate timer here will tell us the time that it takes our 1.9 centimeter marble to pass through the photo gate. So 3, 2, 1. And you can see it took 0.0023 seconds. Whoop. That's okay. I haven't lost my marbles yet, you guys. 0.0023 seconds. So the velocity is this distance divided by time. Oh, don't let me forget, you guys, to show our e-learning colleagues and our YouTubers following along years from now to show them that poster. So we had, let's do it in meters per second. So what is 1.9 centimeters in meters? I heard somebody say 0.019, who's the same person that called out the answer earlier. So divided by 100, right? Because there's 100 centimeters per meter, so 1.9 centimeters is 100.019 meters. And it took that 0.019 meter marble 0.0023 seconds to pass through that photo gate. This is why we can't do it with a stopwatch. So like, all right, everybody start your stopwatches. Like your human reaction time is about half a second. So 0.5, so how could you ever measure that? So, oh no. So everybody with a calculator knows that 0.019 meters divided by 0.0023 seconds is 8.26 meters per second. That's how fast we can launch. All right, so if we launch something at 8.26 meters per second at some angle, how far away does it land? How high up does it go? Those are two questions we want to be able to answer. So here's the physics, the range of our projectile, how far down range it will land. is equal to the x component of its velocity. Like how fast is it moving sideways? Times the time airborne. So it's like, how long is gravity sort of allowing this thing to move sideways? The faster that you launch it upwards, right, the more time it's going to be airborne. So those are the only two things that affect the range of a projectile. How fast it goes this way and how long it's airborne. How long it's airborne is really dependent upon how high up it starts. So note that our marble launcher is 26 centimeters above the lab bench. Our calculations, we're kind of assuming it's going to land as high up as it starts. Well, that's not the case on the lab bench, right? Like we're launching it from a little bit higher up. And so I happen to have here a 26 centimeter tall box, okay, or a 0.26 meter tall box. And so if we want to, we could land on the bullseye, all right? And we'll put this here to avoid the tougher calculation of like, oh, it's going to fall a little bit further than we want it from. We can deal with that, okay? Like we know all the physics to do it, but it makes it a little bit tougher, you know, for on short, Friday. So we're just going to try to land on this box, okay? We're going to make a prediction about where this marble should land. And hopefully we get somewhere close to the bullseye here. So this is exactly 26 centimeters tall. So it's landing at the same elevation we're launching from, right? So kind of think about it like that. It's above the ladder, right? So we need to be able to calculate Vx and T. And we do that by resolving our vector here. So how does that look? I'm going to kind of just move this down here to do a little bit of math with it. So it's going to go, I'm going to launch at 35 degrees, okay? So I'm choosing a launch angle of 35. So I have a vector that is 8.26 meters per second of velocity. At an angle, so a vector has direction, and the angle here is going to be 35 degrees. So now I say, how much of that 8.26 meters per second is acting horizontally? How much of it is acting, we'll do this in tasteful light blue chalk. How much of it is acting vertically? This will be the component that gravity decelerates. And you launch something up to your left, to my right, then it has a component to the right, has a component up. All right. And so the faster we launch something up, the more time it's going to be airborne. If you know a little bit of trigonometry, that's kind of all you need to resolve this. And so there is a side that is adjacent to this angle, 35 degrees. So Coa is the helpful mnemonic device. So Coa. So we can write that because this side is adjacent, and we know the hypotenuse, right? There's our right angle. The hypotenuse is opposite the right angle. We know our hypotenuse is 8.26. That's its actual velocity in this direction. The trouble is that calculation we did a moment ago with gravity only affects this part of the vector. It doesn't care how fast things move sideways. Okay. The famous sort of example is like if you drop a bullet, you fire a bullet out of a rifle, they do indeed hit the ground at the same time. The one that you fire out of a rifle is much further down range, but if they're at the same elevation, gravity acts on them just the same. Okay. And so this side being adjacent, we could say that it's really the cosine function that's helpful. It would be the cosine of the angle 35 degrees is equal to the adjacent side, the x component of velocity, I'm off the charts here, over the hypotenuse, which we know is 8.26. So if I come back here now, we can solve that the x component is just multiply both sides by 8.26, and you have the cosine of 35 degrees times 8.26 meters per second, which everybody with a calculator, so times 35 cosine equals, it's about 6.8 meters per second. So if you launch something at 8.26 meters per second, 35 degrees above horizontal, 6.8 meters per second are going this way. That doesn't mean that like the difference between them is up. That's not the way we calculate, sort of, it's not this plus this equals this, okay? It's a more complicated relationship. It's this squared plus this squared equals this squared, like Pythagoras' theorem. So we could use the Pythagoras' theorem to calculate this, but we'll just keep using the trig. And so this blue vector is opposite this 35-degree angle right here. And so opposite, that's the SO in SOHCAHTOA. You remember that? So we have now the y component of velocity is equal to the sine of 35 degrees times 8.26, right? So sort of setting it up the same way, like the function of the angle equals a ratio of sides. And if we multiply both sides by the hypotenuse, we can solve for the thing we want to know. So the sine of 35 times 8.26 gives us 4.7. 7 meters per second. So we know the initial conditions of our marble. We're going to launch it at 4.7 meters per second up and 6.8 meters per second over. Now we can apply some physics of gravity. So we'll say at the top of its flight, one thing we want to know there is how high up it is. Okay, what's the maximum height? The other thing that we want to know is the range, right? Which we said we can calculate by doing VXT. And so we need another time airborne. So at this point, gravity has slowed this initial velocity down to 0, right? Like it has an initial velocity vector up that gets sort of slower, slower, slower until eventually 0. So we know that the velocity, like at this point here, let's call it like the velocity at max height, you know, whatever helps you know that that point's important, okay? It's 0 meters per second right there. In the y direction, it's still traveling this way, right? Because as we mentioned a moment ago, nothing slows down the fact that it starts out moving 6.8 meters per second this way. So it keeps that same 6.8 meters per second sideways the entire time. So when it's at the top of its flight, yeah, its y component has dropped to 0, but it's still moving this way. Well, gravity doesn't, you know, stop just because it's at the top of its flight. It speeds it back up. And so by the time it lands, it's going just as fast this way as we launched it. Right? Gravity slows it down and it speeds it back up, and you have symmetry of motion. So we can solve for the time it's going to take to get to this point because we know how its velocity has changed. It's changed from 4.7 to 0 under the influence of our 9.8 meters per second squared of gravity. So gravity in this case is decelerating, right? It's slowing it down if we want something up. So you have like this vector, right? Remember, there's planet Earth down here, 5.97 by 10 to the 24 kilograms of mass that's creating this gravity field that accelerates things. 9.8 meters per second every second, meters per second squared. So we'll calculate the time to max height, which is not the total time airborne, right? It's half of that time. The time to get here, we'll call it lowercase t. We can solve like v equals like the v to max height equals the v sort of initial plus acceleration times time. It's sort of like the general equation for it. And we know that the velocity there is 0, and we know the initial velocity was 4.7. Gravity here is negative, okay? If we launch 4.7 up positive, gravity is acting against it negatively. So that vector is negative, and then t is the thing we want to know. Now I have a perfectly solvable algebra equation. You don't subtract 9.8 from this. Okay, don't do that. That's not what you would do in math class. You'd subtract this from both sides, and then divide both sides by negative 9.8. Off the charts again. Maybe. There's that poster over there, you guys. I'll give you a more close-up view. If I remember. So we've got 4.7 divided by 9.8 equals t. which is the time to get here. 4.7 divided by 9.8. Remember that 9.8 comes from somewhere, right? That's how strong the gravity is. So according to my calculations, it should take a time, lowercase t, of about half a second, 0.479. So we'll say 0.48 seconds, which means it takes 0.48 seconds for it to fall. So the total time airborne would be 0.96 seconds, so less than a second. We're going to launch this thing in less than a second. We should hit that box or somewhere close to it. Should say that like this is completely theoretical based on the physics of gravity, or gravity alone, not wind resistance, not how the mechanism, delivers sort of the force to it. Like, are we sure that it's going to be that every time we do it exactly? We're basing our calculations on it. So keep those things in mind. It's not, the difference between theoretical and experimental. Usually they don't agree, but they should be close. So now we have everything needed to determine the range and the height. The height we calculate as 1/2 gravity times time squared. And so this is the time that it took to get up there, which we know. So we can approximate the height to be 1/2 of 9.8 times 0.47 squared, which gives us 4.9 times 0.47 squared. 4.9 times 0.47. We're saying this thing should go 1.08 meters, so 108 centimeters tall. But when will it be that tall? Okay, so we can actually plug in any time to solve for the range. You say, well, what's the range? Halfway. So that would just be the Vx, the component of velocity that's moving sideways, which you may recall is 6.8, times 0.47 seconds. Well, that's going to give us the half range, the range to this point, 3.196 meters, which means double that. And we expect a total range of 6.4 meters, okay? Which would be the same thing if we did 0.96 times Vx, right? Like you could either double the time to get the total time airborne and multiply that by Vx, or we could calculate half the range and double that, right? You get it's mathematically the same. Two different ways to approach the calculation. So we have predictions. It should land 6.4 meters away, and it should be 108 or 1.08 meters tall, 3.2 thereabouts meters downrange. And so now let's go ahead and test our predictions. The last time we've got left. Abbreviated Friday schedule. So I have 1, 2, 3 meters. The apparatus with 1, with 2, with 3, our box downrange. Okay. 3.2 meters. So we're saying right here, okay, this is where it should be at max height. We should have a shortage of rulers. 5 meters. We have 1, 2, this is 3 meters, there's our 3.2. 1, 2, 3, 4, 5 meters. 6 meters. The edge of the lab bench is just about 7 meters away, a little bit less than that. But remember, that thing's sitting on the edge there too. And so we want 1, 2, 3, 4, 5, 6.4 is right here. Okay, now notice it's gonna be coming in at an angle too. So like if it hit, so if it here, but it could also be well short, it could also be long because there's uncertainties in these measurements. But that's our prediction. And we're also predicting that if we go 1, 2, 3.2, 3.2 meters downrange, the projectile being launched should go 108 centimeters, which is, this is 100, right? So that's 1 meter. So about another, okay.
If you do that, once the marbles hit it,
I hope that would be cool if we could get an actual collision. What are the odds of that?
maybe we think it's just start
Yeah, that'd be cool if we got a. We wouldn't be able to get a test of our total range, but I'd be okay with that. All right, so you kind of eyeballs on here, see if that's about where it passes. Instead of having this one marbles down.
Yeah, a little bit.
Here. So you'll see it launch. I think that's the view you want. All right, so I've got the ruler set up here for a maximum sort of height, 108 centimeters above the lab bench, and the box is there 6.4 meters away. 3, 2, 1. Now return to me. I feel like the height prediction was pretty good.
Came back to the mouse.
Just like I planned, all right? But it was a little bit short of the range calculation, right? So it didn't even hit it short of the box there. So you can say, oh, my instinct now tells me that this apparatus is a little bit uncertain. I bet you that's going to be a good shot.
It's like this kid kicked it. Got it.
3, 2, 1.
Oh. Did it get out of the car?
All right, that's it.
Did it get out of the car?
Yeah.
Oh, cool.
Back and around.
Yeah, that's so weird.
All right, so that was still short, right? Couple of minutes. I think we got 44 or something.
It's 37 right now.
So we think sometimes it's like, oh, because it landed here, it's going to land in exactly that same spot again. We move the thing, but it's so sort of it's basically getting there. So that's the point. Like the physics is accurate, but with the uncertainties, it's never perfect. We'll try this again, and we will launch. 3, 2, 1.
Oh.
See what I mean? Like I moved it closer, and it's like, oh, I should have left it there and just fired it again. I don't want to give our e-learning colleagues a cool view here. So There's, keep a close eye on it. 3, 2, 1. Man, I ruined the view over there. I don't even think you can see it. Yep, it perfectly landed in. But we'll have to see that another time.